Ready, Maddie? You look totally psyched. We're going to be looking at one-dimensional force problems today, where everything is in a nice straight line. In a few days, we'll say, what if we're on an angle? Did I say angle? And hopefully you'll be able to figure out the punchline components. Really, I'm going to be not teaching you that there's going to be components. It's which are the best components to use. That's what I'll be teaching you when we get there. Some interesting or important one-dimensional force problems include the elevator or apparent weight problem, the air resistance problem, friction, we'll look at that next lesson, and then the many body problem where you have more than one mass. That was Atwood machines and pulleys and ropes, and we'll look at that a couple lessons from now as well. So we need to talk about the normal force. This was very weird to you all last year. The normal force is the contact force between the floor and the object. Let me pause for a second. So the normal force is the contact between the floor and the object. It's a bit weird because you have to realize an inanimate object makes the force, but it must. Are you sinking into the ground right now like quicksand? Are you flying into like Superman? Then the forces on you right now are balanced, and I know gravity is acting on you. That must mean there's another force the same size as gravity pushing up. That's the normal force. Okay? So the normal force is also the value that a scale would read if you were standing on it. Scales don't read mass. They don't read weight. They read normal force, which means on a test, when I ask you to tell me what a scale is reading, I'm not asking you to tell me what a scale is reading. Which force am I really asking you to find? Normal force. That's a hint, by the way. You're going to have a question like that. And for this reason, the normal force is also called the apparent weight of an object. Your actual weight is mg, but the weight that you feel is the normal force. That's why you're able to feel heavier or lighter on an amusement park ride. We haven't mucked around with gravity. We're not God. We can't control the universe or anything like that. We can change the normal force. So all of you right now feel a normal force that equals gravity. All an amusement park ride does is mess around with the normal force. Put your pencils down and look up. Normal force. If a person with mass, little m, and weight, mg, big W, is in an elevator standing on a bathroom scale, and let's make it a scale that reads newtons, not kilograms or pounds, so we don't have to do any kind of conversion. Let's make it a physics scale that reads newtons. If the elevator starts at rest and accelerates up, what will the scale read? A, W, B, more than W, C, less than W. Maddie's yawning. I know why. She's bored. She wants to exercise her right to vote. And I get that. So since there's 3 answers here, once again we get to vote. Once again, how high you hold your hand up is how sure you are of the answer. So if an elevator starts at rest and accelerates up, does the scale read W, more than W, or less than W? Who says A, exactly W, Mr. Dueck? A. Drew looks around to see who's voting A because he's a peer pressure kind of a guy. Okay. Who says B, more than W? Convince me. Because you're correct. Convince me. You know what, Lachlan? This is a job for a good free body diagram. Let's represent this person with a dot. Now, by the way, I'm drawing the forces on the person, not on the scale. What are the forces acting on this person? Get the obvious one. Gravity. And you know what? Instead of mg, you can put mg, but I'll put in brackets, this question is calling it W for weight. I tend not to use W for weight because W is also work, and W is also watts, and W is also west. So I'm trying not to use the W so much. Which way is this person accelerating according to this question? I'm going to ask you the same question. I want the same answer. I'm just going to phrase it differently. Which way must there be an unbalanced force according to Newton's law, first law? I exaggerate it to make sure it's obvious. Which force is that? Well, it's the ground. What do we call that force from the ground? And what does a scale measure? So based on Newton's first and my free body diagram, normal force scale measurement must be larger. Okay? Write a net force for using explaining your answer. I think a good free body diagram does the trick here. I might jot down a couple of words. I don't know if I was on a test just to make sure Mr. Dueck got what I was getting at. Write a net force equation. Who's winning? Who's losing? What does winner minus loser always equal? F net, but what's F net? MA? What that means is I could give you the acceleration and you could find the normal force. I could tell you the scale reading and you could find what the elevator was accelerating at. Now this is the equation for an elevator accelerating up. For an elevator accelerating down, I would take 2 seconds to jot down a new free body diagram, which would give me my new equation. I wouldn't try and memorize stuff. A 35 kilogram student stands on a kilogram scale. The kilogram scale reads the normal force divided by 9.8, because that's how you change newtons into kilograms. If the elevator accelerates down at 2.25 seconds, A says find the normal force and B says find the scale reading. This is the job for a good free body diagram. I'll represent the person right here with a dot. What are the forces acting on this person, Thomas? Get the obvious one.
Gravity.
Yep. mg. Thomas, which way is this person accelerating?
Down.
I'm going to ask you the same question. I want the same answer. I'm just going to phrase it differently. Which way must the larger unbalanced force be pointing according to Newton's first law?
Down.
So there is going to be a force up, but smaller. I'll really exaggerate it so it's obvious. Which force is pointing up? Okay. Who's winning? As mg. Who's losing? Now this time we're going to let down be positive because it's just more convenient to do it that way. So my equation is going to be winner minus loser. Wow, that erased more than I wanted. Equals m8. Thomas, what does A want me to find?
The normal force.
How would I get the normal force by itself? What's right in front of the Fn?
Mass times gravity.
Right in front of the Fn.
Oh, minus.
I'm going to plus it. In fact, I'm going to do two things at once if that's okay. And here's how I show this, Thomas. I'm going to plus it to that side. At the same time, I'm going to minus the MA to that side. And I show that with two arrows. A couple of years ago, one of my students nicknamed that the swappy dance. So there's the swappy dance. And we get this. mg minus ma equals Fn. What's m?
Mass.
More specific in this question.
35
Yep,
kilograms.
looking at units, and you didn't have me last year, but you'll hear me emphasize this year. It's always worth memorizing what units go with what. It cuts down on your thinking dramatically. I agree with you. 35. How big is G? You know this from Physics 11. And we're not going to put the negative in here. We're just going to put the 9.8 because we let down be positive. In the forces unit, we'll never let the 9.8 be a negative. The winner minus loser will take care of that part of things. Minus 35 times, what's A?
Down at 2.25.
2.25. I got the down taken care of in my winner minus loser shtick. Okay. That equals the normal force. How big is the normal force? Get your calculators out and crunch the numbers. Maddie, what'd you get? It's going to be around 350, take away 70. I think it's going to be in the 200s. 264? Yeah, have some confidence, girl. What is it? All right, to 3 sig figs, 264 newtons. Now, what does B want me to find, Maddie? Now, if the scale read in newtons, then that's the answer. But this is a scale that reads in kilograms. How do I change this to kilograms? So I'm going to, you got 264, is it 264.25? Okay, so I'm going to go 264.25. I'm going to go answer button divided by 9.8. And in kilograms, this scale would read what? Sorry? 27 even? 26.9. What's after the 9? Okay, so 27.0. So, Nina, does this person feel lighter or heavier? They feel lighter. Are they lighter? No, they feel lighter. And this is why I was saying a scale can't measure your mass. It can't measure your weight. It can only measure how hard the ground is pushing up. And that's what we call your apparent weight. Apparently, right now, they feel lighter. It's not their actual weight, but they would feel lighter, apparently. Is that okay? Example 4. What's the normal force for the following object? Okay. What's this want me to find, Drew? This is a job for a good free body. Wait. Did they give me a picture?
Yeah.
Okay, I'm not going to technically do a separate free body diagram. I'm going to label the forces on this picture, which technically isn't a free body diagram, because a free body diagram, you're supposed to represent the mass with a dot. But okay. What are the forces acting on this 5 kilogram mass? Get the obvious one. 5 kilograms isn't the weight. Gravity, mg, is the weight. Yes?
Yeah. Then a force coming down at 15 meters. So
Yep. What else?
gravity.
Now, you already got that. What else? So ready? Is this mass sinking into the ground like quicksand? Is it flying into the air like Superman? Then the forces must be, I'm looking for a word that begins with the letter B.
Balance.
So everything down has to equal everything. So I have a 15 and an mg down. There's a normal force up, and I know that normal force has to be bigger than mg. In fact, I can even tell you by exactly how much. How much bigger than mg does that normal force have to be exactly? It's got to also cancel out that 15. Okay? That's why if Drew was standing on the scale, if I pushed down on his shoulders, like that 15 newtons, the scale would read more, not because your mass has increased.
Yeah.
What is increased? The normal force. Okay? So I would say this. Everything down has to equal everything. Everything down has to equal everything up. And there is your equation. There is no quote-unquote equation for the normal force on your formula sheet. It's always draw a good free body diagram, and you can figure it out. Because you're not sinking through like quicksand. You're not flying into the like Superman. Or if you're on the elevator, you are accelerating, you know who's winning, winner minus loser. Here, since we weren't accelerating, we took a shortcut. We said it's a tie. Everything down has to equal everything up. Yeah. So the normal force is going to be 5 times 9.8 plus 15. I think I can do that in my head. 5 times 9.8 is going to be 49 points, 59. Is it 60, 64? What is it?
64.
Point?
Just
64 even?
Yeah.
Yeah, you're right. It's 49 plus 15, 64 even. Should have had that, Mr. Dueck. And force, newtons. Okay. This next question, I'm kind of reversing it. I'm telling you the net force. We need to figure out any missing forces, and then we need to decide if they're accelerating or not. So let me zoom in on the first one. If I tell you the net force is 0, how big is force A? Has to be 50. This is the power of Newton's first law. How big is force B? Has to be. Is this accelerating? What's the net force on this, Johnny?
0.
So is this accelerating?
No.
Can't be. Now what does that mean? It's either at rest or it's moving in outer space at a straight line, at a steady speed. I don't know which, but I can't say that it's stopped, but I can say it's not accelerating. By the way, Johnny, what's the net force on this diagram right here? Read it to me. Is it accelerating?
Oh, yes.
What's the net force here?
gonna say
Is it accelerating?
yes.
What's the net force here? Is it accelerating?
Yes.
How do I know for all of those? When am I not accelerating? When the net force is? That's the power of Newton's first law. Okay? If I'm not accelerating, I know the forces are balanced. The net force is 0. If I am accelerating, it can't be 0. So now, having said that, hey folks, what's mystery force C? If the net force is 900 newtons up, how big must force C be? Got to be 1100 newtons. Winner minus loser gives you 900. Yes?
Yeah.
If the net force is 60 newtons to the left, how big must force E be? I'll do D in a second, but how big must force E be? It's got to be 300 because there's no up-down force, so the net force there must be 0. Little trick here, if the net force is 60 newtons to the left, Lachlan, how big must force D be? Got to be. If the net force is 30 newtons to the right, how big must force G be? How big must that one be? It's got to be 50. Now, ready? Listen close. How big must force F be relative to force H?
mg.
No. What? So how big is force F exactly? No, it's not however big you want it to be. What, William? Has to be. Otherwise, they aren't balanced.
Isn't mg?
I don't know. I haven't told you that you're on the ground. I haven't even told you that you're on the earth. I can't make those assumptions. Okay? I mean, that force might be being caused by gravity. I don't know. All I'm saying is, if I'm not accelerating up, down, the forces must be, I'm looking for it means letter B. And in this case, if I generalize it, H is the same size as F. F has to be the same size as H. Maybe I can say more if you tell me the context, but right now I have no context. Air resistance is the force of air molecules that are bumping into an object that's moving through the air. And the key concept with air resistance, its direction is always opposite to the motion. If you're moving up, air resistance is down. If you're moving forwards, air resistance is backwards. So example 4, next page. Example 4 says, draw force diagrams for each of the following. A ball being thrown, a rising ball will include air resistance, and then a falling ball, and this time we'll include air resistance. Usually we'll ignore air resistance, but okay. So situation A, look up, we're talking about this. While it's in my hand, put your phone away. Oh, sorry, that's your calculator, my bad. While it's in your hand, on the way up. What are the forces acting on it? Get the obvious one. Yeah, that's the punchline. Gravity, mg. While the ball is in my hand, is it in free fall, moving downwards? It is accelerating downwards. Say no. So there must be a force pointing which way? Is that force going to be bigger or smaller than mg? Which way is the ball accelerating while it's in my hand? Now, if it wasn't bigger, watch. That's going to happen. I moved the ball up, but I didn't accelerate the ball up. For me to accelerate the ball up so that it leaves my hand, that force has to be bigger. I'll call it, I don't know, throw. You could call it a normal force because it's the surface of my hand, but if you want it to be more specific, it's that force there. It's me throwing it. Okay? Mr. Dueck, what, Colby? Wouldn't there be air resistance while it's in your hand? There would be. I'm ignoring it. Let's pretend that somehow I'm covering the ball so that there's no air resistance and I'm going to let it go. I don't want to get into that complicated situation, but you're correct. Now, situation B, is that one there on the way up. This time I'm going to do a free body diagram. I'm going to represent the mass with a dot. What are the forces acting on it on the way up? Get the obvious one. Which way? Yep. What else? Air resistance, which way? Also down. How do I put two down forces on a free body diagram? I tend to put the next one kind of beside it, because if I put it on the same arrow, I might miss it. What else? Or is there anything else? Maybe there isn't anything else. Is that a hand up?
Yeah, the acceleration upwards.
Acceleration isn't a force. It doesn't go with my free body diagram. And by the way, are you telling me this is speeding up on the way up? It's accelerating upwards? So I'm going to say, You okay with that? In fact, it's moving up, but it's slowing.
Down.
So which way is it accelerating? The two forces that I'm there, would that cause something to accelerate down? The two forces that... I think I'm okay with this. There is no upwards force. Okay? C. What are the forces acting on it? Get the obvious one. Gravity? What else? Which way? Bigger, smaller, or the same size as mg? Because on the way down, which way is it accelerating? Which way is it speeding up? Is it speeding up going up? It's speeding up going down, so there must be a smaller force. Now, air resistance is really difficult because it's always a changing force. I'm going to talk about that in a second. But just for this little toss here, we're keeping it as simple as possible. Oh, but here's a question. In 4B, how can the ball be rising if all of the forces are downwards? That's a good question. Thomas pointed this out. How can the ball be rising if all the forces are downwards? What does the net force tell us? As if I want to solve it, but what does the net force tell us about acceleration? If the net force is up, which way is it accelerating? That's Newton's first. If the net force is left, which way is it accelerating? If the net force is right, which way is it accelerating? If the net force is down, which way is it accelerating? So all that the net force tells us is the direction of the acceleration, not the direction of the velocity. Velocity and acceleration are independent. This is a tough one because kids get velocity and acceleration mixed up all the time. They want to look at that middle diagram and they want to say, Mr. Dueck, doesn't that have to be moving down? No, it has to be accelerating down. But if you give it a big enough up speed, it's going to keep going up for a while. It's going to be slowing down. Eventually it'll come to a stop, change direction, and then start to move down. So I want to write that, but not in a big paragraph. How about this? Velocity is independent of acceleration direction. That's really hard to read because it's right halfway through a line. Can I do that? A little better. All that Newton's laws tell me is the direction of the acceleration. They don't tell me the direction of the velocity. Now, if I keep accelerating long enough, the velocity will match the direction of the acceleration because eventually you'll slow down, come to a stop, turn around, and start going in that direction. But here in this snapshot right now, I'm okay with that. I'm not breaking any physics laws. If the ball in example C is speeding up, write a net force equation. Drew, in example C, this was your equation, who's winning? How do I know? From the free body diagram, longer arrow. And how did I know to do that? That's the way that it's accelerating. Newton's first. So winner minus loser equals MA. Okay. Example 7. a 90-kilogram parachutist free falls for a time. Eventually, I jumped out of an airplane. And then opens a parachute. If the parachutist slows down at a rate of 1.5 meters per second squared, A says compare the forces that act on the system. That's physics code for, this is a job for I'm going to do a free body diagram to compare them. Okay? So A, what are the forces acting on this parachutist? Get the obvious one. And by the way, the reason I do that is everybody wants to jump to, well, the parachute relax. We'll get there when we get there. But by getting our forces in a row, it helps us figure out who's winning. It helps us use Newton's first. So get the obvious one. If I was in free fall in a vacuum, that's it. Am I in free fall in a vacuum? Okay. So there's got to be a force up, bigger, smaller, or the same size as gravity. Let's see if we can figure it out. The key phrase, you might want to underline this, slows down. Johnny, which way is this parachutist moving? Down. Are they speeding up or slowing down? So here's the question, folks. Which way are they accelerating? Maddie, which way is the winning larger force have to be pointing? Upwards. You okay with that? What force is that? Air resistance. If you've ever watched skydiving videos, or if you've ever gone jumping out of an airplane yourself, I mentioned I jumped out of an airplane. This is right after you pulled the parachute. You are slowing down, which means the winning force must be pointing up. For that split moment, air resistance is larger than gravity. It's what's slowing you down. So B, Johnny, it says write a force equation. Who's winning? Who's losing? What does winner minus loser always equal? Which is just MA. Good. Good. Victor, what does C want me to find? How would I get the F air by itself? I would add mg. Yeah, leave F air there, add the mg over. By the way, if I minus F air, then I'd have a minus F air on the other side. I'd have to deal with the negative. It's doable, but the simplest, yeah, let's get it by itself here. So you're telling me, and you're right, air resistance is equal to MA plus mg. Victor, this question give me the mass? What is the mass? Yep. Did they tell me the acceleration? How do you know? Meters per second squared. Mr. Dueck, is that positive or negative? You don't need to worry about that. If you set up your free body diagram and done winner minus loser correct, we're just plugging and chugging. There's a minus sign. You said the mass was 90. Sorry, plus sign, not a minus sign, a plus sign. What's G? Yeah, and not negative. We took care of that in our winner minus loser shtick. What's the answer? I might be able to do this in my head. I can factor out a 90. It's going to be 1.8 plus 10.8, 11.3. So it's going to be 990 plus 27. Is it 1,017? Yeah? So 1,020? Drew gets impressed every time I do that. But it's true, so, you know, tying your shoes sometimes might impress him. Okay. Now, the reason air resistance is so tricky, it's not a constant value. It gets larger as speed increases. You may have tried this when you, if you're a passenger in a car or in the back seat of a car, put your hand out of the window on a nice sunny day with your hand like this and then tilt it sideways, and you'll notice the force changes. It depends on the cross-sectional area and how fast you're going. The faster you go, the more air resistance. The smaller you go, the less air resistance. So here, in this situation, as he slows down, air resistance gets smaller. And in fact, eventually it reaches an equilibrium point where air resistance is the same size as mg. We have a name for that. Anybody know what we call that steady speed when you've maxed out your maximum speed when you're in free fall? It begins with the letter T. This is terminal velocity. And terminal velocity, Thomas, depends on many things. It depends on your area. It's why skydivers traditionally go in that spread eagle, maximize your cross-sectional area position. But if I want to fall faster, I would tuck and go vertical. All a parachute does is dramatically increase my cross-sectional area. I'll hit a new terminal velocity, but hopefully one that isn't terminal, so to speak. Another one that I can survive the landing on. Okay? So what would the force of air resistance be once terminal velocity was reached? And why can I say that? If you've reached terminal velocity, what's your acceleration? And so if you go back to this equation and you put a 0 right there, Victor, if you put a 0 right there, you'll end up with F air equals mg. That's terminal velocity. Parachutist jumps out of a plane and free falls. Imagine they jumped out of an airplane. They reach terminal speed and then they maintain that speed for a while. They then open their parachute. They quickly reach a different terminal speed and descend to the ground. Sketch, can you cross out the word velocity? We're going to make it a speed time graph. And the reason is velocity would be negative, which means that my graph would look like this below the x-axis, and I'd rather have it above. So we're going to graph vertical speed. This graph here, that got way smaller all of a sudden, is not going to be accurate to scale. The shape is going to be right. The scale is going to be garbage. So everybody, let's go like this. On the x-axis, let's put t. On the y-axis, let's put Vy. All right. I'm sitting in the airplane right now, but I haven't jumped yet. What's my vertical speed right now? Yep.
0.
So there would be a stretch, probably longer than I've drawn, but there would be some time when I was psyching myself up. I jump. Ah! What happens to my vertical speed? Increase, decrease, or stay the same? Increases. Okay. So my vertical speed maybe goes there. Now here's the question. Don't write this down. Does my vertical speed increase at a constant rate? When am I accelerating the most? Right when I jump, what's my air resistance?
0.
So that's when I'm accelerating the most. But as I accelerate, what happens to my air resistance? So my net acceleration decreases. I think it would look something like this. And then I plateau off, and right there is my terminal speed. And it increases at its maximum right there, but as air resistance gets bigger, I don't speed up as fast. I pull my parachute, now what happens? Speed up, slow down, or stay the same? Slow down. Okay, so my speed's going to drop to like somewhere here. Right when I pull my parachute, is air resistance the biggest or the smallest? It's the biggest. I think it would look like this. And then I would do this, and here's where my diagram is no longer to scale, because I remember when I jumped out of an airplane, eventually I jumped out of an airplane, that the parachute, the free fall was about 30 seconds, the parachute part was about 5 minutes, so really this line should keep going to the right and extend to the far wall, but I'm just not going to worry about that. So here is me drifting down, another terminal velocity, but this is the survivable one. Then I hit the ground, what happens to my vertical speed? Something like that. Something like that. I'm not going to ask you a question like that, but it's a nice little intellectual exercise. I know I've done this one right, because from the side, it always looks a little bit like a VW Beetle, sort of. This is the Beetle graph. Who's in calculus? You'll start doing a lot of graphing like that as well. What's your homework? Number 1. Number 2, Number 3. 4 is good. 5 is good. 6 is good. 7 is good. Skip 8. 9 is good. 'What have I got here? Yeah, 10 is good. 11 is good. 12 and 13. Skip 14. And if you want to, you're now capable from the ultimate vector dynamics assignment of doing those questions there if you really want to. But we've been talking about free fall.